Hello everyone, this is Angelmouse here, and today we will be reacting to the theorizer. That's right everyone, this is the reboot of the Angelmouse React series. I haven't done this in a bit of a while, so let's get right into this. Today, for this episode, we will be reacting to 4 videos made by the theorizer, all of which will be different. So, no more talking and babbling. Let's get straight into this. I am so excited. Let's go.
Yes, we've all seen Pixar's Up. I mean, who doesn't like a balloon-powered bungalow? Me, I hate the physics of this film.
Yep.
Pixar's even admitted to having greatly under-exaggerated the amount of helium used. They claimed it would take up over 23 million large helium balloons to lift Carl's 1,800 square foot habitation. So, if this is the case, how would real-world helium physics apply to lifting other structures? First, let's establish how this works. All helium balloons use a force known as buoyancy to float. Basically, if there's an object that is less dense than the surrounding fluid, it will try to rise above it. And if you don't know, density is how hardly packed something is. A few obvious examples are wood and water. Even if you have an extremely heavy dock, it will float, because wood isn't as dense as water. Another example is with bubbles. Air isn't as dense as water, so air bubbles rise to the surface. The only exception to this is when it's a very small object like a paperclip. The paperclip is a metal and is more dense than water, but sometimes it will float. Why? Well, it's not actually floating. It's just sitting on a thin layer of the top of the water known as the surface tension.
Oh my god.
But getting back to our balloons, they work quite in the same way. Helium isn't as dense as air, so when balloons are filled with helium, they rise up until they're above the air. So to find out how many balloons we need to lift any given object, we need to use a little formula I created that I like to call buoyant lift. All we need to know is how big the balloons are, what they're filled with, and how heavy the object they're trying to lift is. L sub R is something known as the relative lifting ability, which basically has to do with the density and floating part of buoyancy. In short, it's basically the difference in densities. In water, the density of water minus the density of wood. In our case, the density of air minus the density of helium. Typical air density is around 1.225 kilograms per cubic meter, and typical room temperature helium gas has a density of 0.1664 kilograms per cubic meter. Subtracting gives us our relative lifting ability, 1.0586 kilograms per cubic meter. Next, we need to know how big each balloon is. I'm not going to assume one giant weather balloon because,
weather balloon's big.
That would be stupid, I guess. Anyways, average party balloons can be up to 1 foot wide. Dividing by 2 and putting it into the volume of a sphere formula gives us a volume of about 0.015 cubic meters per balloon. If we multiply the bottom of my formula, we can get a very nifty number to make everything quicker. So now all we need to know is how heavy something is, and making sure it's in kilograms, we just divide it by 0.015879. So, what kind of structure should we use, and how do we find the weight? Well, on average, a building is 50 pounds every square foot. Now, this is a death by cringingly painful estimate, but it's all I've got. Let's start with a large house, namely, one with 3,000 square feet. Multiply it by 50, convert to kilograms, divide by our...
Correct me if I'm wrong, but, I believe a mansion has to be, 4,000 feet per square foot, or something like that, or 40,000 square feet to be considered a mansion. Yeah, correct me if I'm wrong with that, but, yeah, I think I think that's how big the house would need to be if it were ever needed to be considered a mansion. Yeah. Plus, I think the way how they calculate if it's a mansion or not is by layering all of the the rooms, like laying them all down and figuring out how long or how big the house would be if it were like built like flat, like 2D house. But that'll never happen because 2D houses are impossible. I mean, houses have length, width, and depth to them. That's why they're 3D. Alright, enough rambling, let's go back on video.
Constant, and that turns out to 4,290,000 1-foot wide helium balloons. 4.29 million balloons will lift a large estate off the ground. But really, this is only if the house is sitting square feet. Multiply it by 50, convert the kilograms, divide by our constant, and that turns out to 4,290,000 1-foot wide helium balloons. 4.29 million balloons will lift a large estate off the ground. But really, this is only if the house is just sitting there. This is only if it isn't attached to the ground. It would only take this many balloons if it was dropped onto the ground without a foundation and then lifted back off. And unfortunately, involving the strength of the foundation gets way too complex for a video like this. Yikes. And there is nothing fun about analyzing virtually hundreds of tensile yield and ultimate tensile strengths of the concrete base of a mansion just to find out how much force it would take to rip a house from the ground. Okay, so sure, a small mansion would require 4.29 million balloons to lift it. So, let's get bigger.
Oh, yes.
I present to you the house of the currently richest man on the earth, Bill Gates. This house's name is, X-Han-Zan.
That guy's so rich he could probably buy more than a million Big Macs or something like that. The average price of a Big Mac is probably, correct me if I'm wrong, maybe $2? Or, no, it's not on the dollar menu at McDonald's. It's probably higher or something. I don't know. But, yeah. That guy is so rich he could probably buy more than 1,000 Big Macs. Or something. I don't know. Why can't he use the money for something much better? Like, maybe the educational system? Better security? Unless that's decided by the government or US president, then why can't he do that? Why? Alright, enough rambling, let's go back onto the video.
Xanadu. His Washington home, or I guess his country club with a population of a few, is approximately 66,000 square feet. This is around 3.3 million pounds, or 1,650 tons, and would require 94.46 million balloons.
Oh my god.
Stop. That's not actually that much, or at least in comparison to the largest house in the United States, Biltmore House, which contains 135,280 square feet. A structure like this weighs 3,382 tons, according to our 50-pound conversion.
That's a beautiful house right there. That's a big house. How is that even considered a house? That looks like it could be considered a mansion. No, not a mansion, a super mansion. It looks like a super mansion. It might, on the outside and possibly the inside. Never mind the person in the background. Please ignore them. Yeah, that looks like, that could be a super mansion probably. Or just a mansion, I don't know. But yeah. let's get back onto the video. Let's go.
And will require 193,620,000 helium balloons. America for the win.
Oh,
Yet,
definitely.
my hunger turned obsession for massive numbers.
We need big numbers.
So I stopped with houses. I present to you the Walmart Supercenter, providing you a great value needs since 1962. Because if you save money, you surely live better. This unnecessarily complicated behemoth of a store is 3 stories tall and 260,000 square feet. Because there's 3 stories, we'll need to multiply whatever weight we get by 3 for a more accurate approximation. So this nearly 20,000 ton complex would need 2,460,000,000 helium balloons.
Oh.
Since I still feel unsatisfied with that number, I'm jumping into the region of physical impossibilities. The only other thing I want to do is planet Earth. If the Earth was placed in an atmosphere big enough with the same properties as Earth's atmosphere, it would be lifted with 376 septillion balloons.
Hold up. That's a big number, and I'm gonna count how many zeros there are. So 3, 6, 9, 12, 15, 18, no wait, no. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24! 24 zeros after the number. Jeez! That's a lot. That is a lot of balloons. And I imagine the cost would be very, very, very large. Even though balloons are probably cheap. Like, maybe like you can get like a pack of like 24 balloons for maybe like, at best, $2 to $4. Right? Yeah, the cost is gonna build up. Let's go back in.
That's 376 000 000 000 000 000 000 Okay, you know what? I lost track. Just read on the screen. It's ridiculous.
Yep,
balloons.
very ridiculous.
So Pixar's film isn't correct, but it could be. With a little more effort, I'm totally sure mankind can and will concentrate all of helium's existence on Earth into septillions of latex spheres. Please subscribe for theories every Sunday morning and Wednesday afternoon. And share, share, share. Until next time, I'm the theorizer.
Question: Does making a video, does making a reaction video count as sharing? Yes! It probably does. You're actually correct, voice in the background. Alright, a little bit of promotion. Subscribe to the Theorizer. They're great.
To me.
No voice in the background. Subscribe to the Theorizer.
Or subscribe to the theorizer.
Yes, exactly. Subscribe to the Theorizer. They make great videos. Let's go into the next video, y'all.
Will I play more videos?
That sounded terrible. Alright. No, you need to make it quieter. Make it quieter, not louder. Alrighty. Now we shall go into the next video. Oh, awesome. We got a new subscriber. Hi. Let's go. And welcome back. This is our next video. This video is going to be about who is the strongest character in the Super Smash Bros. Franchise. I'm actually very curious. Now, let's get into this.
Ever since I analyzed Kirby's Ice Breath in Smash Bros. 4, I've set out to find the most powerful character. Not necessarily the most deadly or strongest, but the one who can hit the hardest.
Ooh.
And in all of my research, I discovered which character is the most dangerous. Ganondorf. With his move, Warlock Punch, he can KO anybody very quickly. The world record distance for the sandbag hit is over 40,000 feet. using Ganondorf.
Wow.
After the percentage of the sandbag was brought up really high, it was Warlock punched. I'm going to assume that this is the peak ability of this move. So without getting into too much detail, here's what would happen if you were Warlock punched. Timing the sandbag's flight using projectile motion equations, calculating the initial velocity, and that turns out to Ganon punching with 472.26 meters per second, or 1,700 kilometers per hour.
Wow.
That's almost Mach 48. If the sandbag is roughly 5 feet tall and 1.5 feet in diameter, and is full of sand, it weighs 355 kilograms.
Jeez.
This fist produces 39,587,737.6 joules of energy. Let me translate that. If we can assume a foot or so of punch into the sandbag, then Ganon punches with over 130 million newtons, or 29 million pounds of force. If Ganon has a rectangular average-sized fists, that's 3.5 million pounds per square inch.
That's gonna
hurt. It accelerates with nearly 45 million times the gravity on Earth. Since the air resistance on the fist is extremely high due to its immense speed, the fist would produce 1.6 million degrees Celsius.
That's hot.
Or 2.9 million degrees Fahrenheit. With a wind resistance energy of nearly 722 million joules during the 0.5 seconds that the fist is punching. If its drag kinetic energy was converted into electrical energy, it would have 1,443,000,000 watts, which could power 1,156,430 houses for the half a second that it is doing what it is doing. Thanks to the heat, anything wood or more easily flammable within a 275-foot distance would burst into flames, and if its electricity were hitting...
My paper bursting into flames would be a nightmare for me because I am an artist. I like to make art. It's my thing. Might add a little thing at the end, like secret thing. Tell you guys like a secret thing for theorizer if you're watching. Yes, let's do this. Let's keep watching.
A human, it would be lethal, as it has 120 amps and 12 million volts, and only 0.1 amps will kill a human.
Yikes.
So, wow. This much drag energy would create an explosion about 16 feet in diameter, and if this move was used in a populated area, it would kill an estimated 5,730 people and injure another 12,740. But if all the energy was concentrated into a noise or sound, it would produce 186.62 decibels, enough loudness to cause pain, instant deafness, and possibly even death.
Oh no.
This is nearly 100 million times louder than an up-close chainsaw and can theoretically be heard from 2.14 million kilometers away. Insane.
Yep.
So, in summarization of this rather quick theory, if you want to create a Warlock punch yourself, you'd need to consume 16,805 McDonald's Big Macs until you'd have enough energy.
I think that'd be possibly unachievable unless you're the guy that eats a Big Mac every single day. Yep, I'm calling you out, person that eats Big Macs every day. Not like literally, like ever since you were born, you eat like a Big Mac every day. Oh my lord, that's a lot. I'm not offending anyone that eats Big Macs or McDonald's because I love McDonald's myself. It's one of my favorite restaurants after all. I'm not ashamed to say that. Question time. What is your favorite restaurant? Please put in the comments below. I would love to know. Yeah. No more rambling. Let's get back into this video.
Although, by the time you'd eaten only a few, you'd likely throw up all the power. Until next time, I'm the theorizer.
It's very childish of me. Doesn't matter. Alright, again, go subscribe-y. Click that subscribe button and also hit that notification bell if you're actually interested in watching theory videos because I would be happy to see the theorizer hit 1,000,000 subscribers. I would actually like to see that. That would be very exciting and like obviously subscriber special. Yes! Alright. Now on to the next video. Quickly right here. Hello everyone, and this is the third video that we will be watching. It is how fast would you have to swim to evaporate all of the water in a swimming pool? Dun dun dun! I don't know the answer to the question, and I am like so curious right now. So let's get into the video. Oh, quickly, I'm gonna get something to eat. So be right back. And I'm back from getting my snack, so let's jump back into our next video. Let's zap ourselves into this.
How fast do you have to swim to evaporate all of the water around you?
Wow.
Don't worry, it isn't too complicated. First of all, usually all energy is conserved. If you have a lot of heat energy, that amount can be fully converted into light energy. Pretty basic.
Wow.
So, kinetic energy, the energy created by movement, will have the same amount as heat energy, just as an example. So swimming movement energy is the same as swimming heat energy.
Whoa.
Okay, so far so good. I'm sure you might have possibly maybe noticed, but water is just a tiny bit harder to move in than air. Since water has quite a bit of resistance, we need to find out how much exactly. And if we know the heat energy, we can divide it by time to get power. That's pretty understandable. Power is the same as energy divided by time. And as a matter of fact, force is equal to power divided by velocity. So our drag or resistance force is found like that. However, the main equation used to find this is displayed here, and we need velocity. So combining it all and rearranging, we find this. It may look intimidating as this abomination, but it's pretty basic. It's just how fast you need to swim to evaporate all the water around you. Here you can see bits of the heat energy and evaporation energy, as well as drag. It's all just mixed in together. M is how heavy the water is. It's volume times the density of water. C sub P is just the specific heat capacity of water. How resistant is the water to various temperatures? Pretty resistant, I'd say. You don't often see water bursting into flames.
Wow.
T sub F is the evaporation temperature of water. How hot can water get before turning into a gas? T sub I is how hot the water is initially. If it's inside, then it's room temperature. Capital L is the specific latent heat of water's vaporization. It's basically a number that corresponds to evaporating water. T is the time it takes to fully evaporate it all. Lowercase l is the length of the arm that is swimming. R is the radius of that arm. And C sub D is the drag coefficient of the arm, basically a number that corresponds to its abnormal shape. The Greek letter rho, which looks like a P, is the density of the water. Finally, V is how fast you need to swim. So what can we find out? It's very easy. Average arms are 28 inches long, or 0.71 meters. They are 4 inches wide, or have a radius of 0.05 meters. I'm assuming you'll be able to vaporize all the water in just 1 second, and that the pool is at room temperature, 25 degrees Celsius. Now it gets a bit trickier. The drag coefficient of an arm, like this, is 0.47, or at least according to online sources it is. And these two heat values are also able to be looked up. Exactly how resistant is water to heat, and how much heat does it take to vaporize all water? Turns out they're 4,200 and 2,258,000.
Wow.
Since water boils fully at 100 degrees Celsius, that's the minimum final temperature. And finally, the measurements of the pool. If the pool is 25 meters long, 20 meters wide, and 12 feet deep, then its volume is 1,820 cubic meters.
Whoa.
And since water is 1,000 kilograms per cubic meter, the pool weighs 1.82 million.
Sorry for the interruption, but now let's jump back right into this.
Million kilograms. That wasn't so hard. Or was it?
Ooh.
So now it's just a matter of pulling out my busted and rusted, yet subsequently trusted, solar-powered calculating device. And you'd need to swim with 20,276.4 kilometers per hour.
Oh.
According to rotational physics, that's 2,525 full strokes every second. But, unfortunately, the vaporization is mutual, as 100 degrees Celsius will likely kill you instantly. But hey, at least you went out on fire. Ha ha ha! I guess you could say that he was steamin'. And unfortunately, steam burns are the worst of all burns, and when what's left of your body will be discovered, you'd be skinned, swollen, and pretty much flattened. You'd have broken the sound barrier 16 and a half times over, thus creating a shockwave that will shatter all the windows in the building, and you'd create waves so unbelievably high that they'd flood out of the building.
Yikes.
After all, what's left of the 1.82 million kilograms of water that hadn't evaporated would have to go somewhere. The energy let off could be enough to create a fireball 528 feet wide and a total explosion 2.86 miles wide.
Oh my...
In a blast like this, in a populated area, 25,140 people would be killed, with an additional 60,810 being injured. The sound alone would be deadly, as it is 10 million times louder than a jackhammer. Swimming this would burn over 1 billion calories in only a second. So basically, it would be the most epic thing to do. Not only would you evaporate a pool, but you'd do something never done before. You'd blow up an entire town with your speed alone. Until next time, I'm the theorizer.
Okay, so technically, I'm guessing if you swam that fast, you would explode. Like it would explode. Like you would explode. Wow. That's amazing. That shocked me. That surprised me. That I can't talk right. Alright, let's do the last video. Let's do it. We can do it, you guys. Let's do it. One last video. Let's go. Alrighty, we are on to the last video, and this one's going to be a fun one. This is going to be about one of the greatest things that I thought, one of the greatest things that I like. One thing that I like is Wheel of Fortune. So if you like Wheel of Fortune, this is the video for you. The video is called How Likely Are You to Win at Wheel of Fortune? Let's watch.
So, I was watching Wheel of Fortune, and as many people obviously do, I wondered about what my chances were of going in there and randomly guessing my way through to the million.
Whoa.
And since I do have a theory channel, I thought why not share my results. There are mathematical operations known as combinations and permutations. How many different ways can you organize a bunch of something? For example, if you have red, blue, green, and pink, how many different ways can you order them? Red, blue, green, pink, red, green, pink, blue, you get the idea. And so you don't have to count out all the possible placements.
So
there
it's
are
like
formulas.
possibilities.
This applies to Wheel of Fortune. There are 26 letters in the English alphabet, and each board has an average of 26 spaces.
Wow.
That is surprisingly coincidental. Anyways, the formula for this is displayed here, where N is the number of possible letters, and R is the total slots. This is a permutation. And since they're both 26, it looks like this. Pretty funny looking. Oh, cool fact, it can also be written like this, and this is called a tetration, although that's for another day entirely. Look it up if you'd like. Anyways, calculating this gives us our number of total possible guesses for one round of Wheel of Fortune.
Hey! That's amazing. Hey! Get hacked. But this is true for me. This is 100% true. The theorizer is awesome. Might be biased over here. This decision is sort of biased. Alright, let's go. Back in. Let's hop in.
6.16 undecillion. That number looks like this, stretched out.
Oh my god!
But that's only for one round.
Whoa.
And since Wheel of Fortune averages at 8 puzzles per episode, simple multiplication lowers the stakes even further and makes it 49 undecillion. But we're talking the million. So what's your chance of spinning the million? Well, there are 26 spaces on the board. So you've got a 1 in 26 chance. Also, factoring in the bonus wheels, 24 spaces, and merging the low probabilities together in with our extremely low probability, we're left with how likely you are to win Wheel of Fortune by winging it. And if you pick random letters and blurt out a random sentence on your first try throughout all 8 games, hit the million card on your first spin, and randomly spin the million slot on the bonus wheel, you'll have a 39/0th chance of winning.
Oh.
How infinitesimally underwhelming.
Is it Alex Karras in Webster?
I don't believe it.
Oh my god, I just took a shot in the dick! Holy crap!
That. Oh my god. That's incredible.
Peter Griffin, truly you are an underachieving genius. Until next time, I'm the theorizer.
That was incredible. He just guessed, and that was amazing. That was amazing to see. Alrighty, so this is the end of the video. So this is the end, and I'll see you in the next one, you guys. Hope you had fun watching this, and we'll see you in the next episode. Hey, bye-bye.